Hello and welcome to another one of these ADD videos. Today we're going to be looking at the concept of flux. What is flux? Well, flux is a way of looking at our electric field lines and trying to quantify them and get an idea of what's going on so that we can maybe calculate electric field. So we're going to be using imaginary Gaussian surface, which is going to be a 3D shape around whatever charge or groups of charges or even sheets or wires of charges that we have to obtain the flux. And we're going to have two basic formulas. One formula for the flux is going to be EA, where this is a dot product. And if you remember, the alternative definition for dot product is the magnitudes times the cosine of the angle in between these two things, where E is electric field and A is a perpendicular vector to your surface. It has to be perpendicular. All right? And if the angle is 0, we're going to have just E times A, but if it's 90 or 270, then it would give you a 0 for those values. And 0 times anything would be 0, so there would be no flux at 90 degrees. If these two things are 90 degrees to each other, no flux. The second formula is going to be the Q enclosed, which is the charge enclosed inside your 3D shape we were discussing, over the constant of permeativity in vacuum or free space. And that's going to be 8.85 times 10 to the negative 12 meters squared per Newton Coulomb squared. All right? That's the formula, and what we're going to be doing throughout this chapter or throughout this concept is setting this formula for flux equal to this formula for flux. And you'll get EA equals that, QE over epsilon naught, and we're going to be discussing wires of charges with linear charge densities and sigmas, which are sheets and stuff like that. So get familiar with stuff other than point charges. This is what you're going to use. We had the Coulomb's law for electric field, which was the KQ over R squared. But here, if we use these, we can get it for something besides a little point charge. Flux depends what the charge is inside your 3D object. So if there's no charge inside your box, your 3D Gaussian surface, then there is no flux, there is no electric field inside here. Also, if the sum of your two charges is equal to 0, there's no net charge, then it's just like it was with this empty box here with no charge, right? So there's no electric field or no flux. If the source of your charge is outside your 3D shape, we have a charge density here of sigma. That means the Q enclosed over the area, the surface area here. And this is a negatively charged conductor. So the electric field lines will go towards this negatively charged conductor. And if you take your Gaussian surface and you put it outside of the source of the charges, then whatever electric field line comes in is also going to come back out. So in essence, it'll be no net charge, no electric field, no flux. So if there's nothing in there, if they add up to 0, or if the source is outside, all those scenarios give you a flux of 0. Otherwise, what you're going to be doing is setting these two flux formulas, EA equal to Q over epsilon naught, and using the respective definitions to find your electric field for any shape. Make sure that if you use a cylindrical Gaussian surface, that the length of the wire far exceeds the radius. Alright, so that should have cleared up any confusion you might have on flux. Enough at least for you to try some problems and get some questions. Also remember to check out your example videos, pause them before you look at the solution and attempt the problem, then check your answer. Practice, practice, practice is the best way to understand this stuff. There's no real way around it. Thanks for watching. Have a nice day.